Picture a billing API on a bad afternoon. A bot slams login from every app server at once. The counter in Redis climbs until the budget is gone. At the same time, a customer double-clicks Pay, and two servers both try to charge invoice 42. Redis gives you two tools, a shared counter every node increments, and a short-lived lock so only one server runs the charge. The bot does not send all its traffic to one machine. 5 app servers sit behind a load balancer, and if each server keeps its own count, every node only sees a slice of the attack. Put one counter key in Redis and every handler increments the same number. When that number crosses your max, every node rejects. The budget is truly shared. The simplest rate limit is a fixed window, 1 bucket per user per minute. The first login attempt increments the key and you set a 60-second expiry. Every later attempt in that minute bumps the same counter. Cross your max and you reject. Watch the time to live tick down. When it hits 0, the key vanishes and the next increment starts a fresh window. Fixed windows are easy to reason about, but watch the edges. A client can fire 100 requests in the last second of minute 1, then another 100 in the first second of minute 2. Each window looks fine alone, yet 200 requests landed in 2 seconds. That is the boundary burst, why teams move to sliding windows when they need smoother fairness. A sliding window log keeps every request on a timeline. On each hit, drop dots older than 60 seconds, add the new one, and count what is left. That count is how many requests truly landed in the last minute, no boundary cheat. The trade-off is memory. You store 1 entry per request and trim on every hit. The sliding window counter buckets time instead of storing every request. Each second gets a field in a hash. Increment the current slice, expire old slices, and add the field still present. You get much of the fairness of a sliding log without 1 row per hit. Back to billing. Tab 1 hits server A, Tab 2 hits server B. Both read invoice 42 as unpaid and both call the payment provider. Without coordination, you double charge a real customer. You need exactly 1 winner, and the lock must expire if the holder crashes. Generate a random token. Try to set the lock key only if it does not exist, with a 30-second expiry. Server A gets OK and owns the lock. Server B gets nil and must back off. The expiry is a safety net. If A crashes mid-charge, the key disappears and another server can try later. Deleting the lock key blindly is dangerous. Imagine A runs slow, its expiry passes, and B acquires a fresh lock. If A finally finishes and deletes the key anyway, it steals B's lock while B is still working. Compare tokens first, only delete if the value still equals mine in one atomic script. And still design the charge to be idempotent. A real pay endpoint often needs both guards. Rate limit per user so the bot cannot hammer login forever. Acquire a per invoice lock so 2 tabs cannot double charge. Do the payment inside the lock, then release with a token checked delete. That's all 13 lessons of the Redis course. Subscribe to Runtime Atlas for more backend engineering deep dives.